I'm the team leader of the Team 16. Our project is a low-cost, lightweight, smartphone-controlled, 50-watt solar panel system with high solar alignment efficiency. The main purpose is to improve solar energy collection by keeping the panel better aligned with the sun. Our team has 4 members. I handled coordination, planning, task distribution, risk analysis, and final integration. EREN worked as software engineer, KAİN as the hardware engineer, and ENHAR as the system engineer. We divided the tasks according to these roles. EREN focused on ESP32 software and Firebase-based control. KAİN focused on hardware components, actuator selection, and cost data. ENHAR focused on level 0 and level 1 design interfaces and system consistency. This Gantt diagram shows our project schedule. We follow the design process step by step: team formation, needs identification, research requirements, and concept generation, detailed design, testing, risk analysis, cost analysis, and final report preparation. The objective tree shows the main goals of the project. These are high alignment performance, smart control, low cost, portability, safe power operation, and practical implementation. This helped us connect the customer need to clear engineering requirements.
Fixed portable solar panels cannot keep the best angle with the sun during the day, so collecting energy decreases. Industrial trackers solve this, but they are too heavy and expensive. Our need is a low-cost, lightweight, smartphone controlled 50-watt solar panel system with 90% peak alignment efficiency. Our requirements are affordability, portability, high alignment, smartphone control, and safe operation. Technically, this system uses a 50-watt rated panel, dual-axis movement, smartphone commands, and stable low-voltage DC power. For the cost, we selected accessible components: ESP32, MG996, R servers, PCA9685, LM2596, INA219 LDR sensors, and frame materials. The estimated cost is around 3,300 Turkish lira. The main risks are weak motor torque, LDR errors, Wi-Fi or Firebase problems, and voltage safety. If the servers are not strong enough, our plan B is a geared motor, stepper motor, or scaled demonstration. Finally, the system should stay low cost, portable, safe, and easy to assemble. For future use, CA, EMC, RoHS, wireless standards, and data privacy should be also considered.
At level 0, the system is shown as one main module. It takes sunlight, smartphone commands, sensor data, and system status as inputs. It gives regulated power, optimized panel orientation, monitoring data, and warning information as outputs. At level 1, we divide the system into main subsystems: the 50-watt solar panel, LM2596 regulators, GL5528 LDR sensors, ESP32 controller, PCA9685 driver, MG996 R servers, Firebase, Wi-Fi interface, and mechanical frame. At level 2, we define the final components. ESP32 controls the system, LDR sensors detect sunlight direction, PCA9685 drives the sensors, servos, and INA219 measures voltage and current. MG996 R servos are selected, but torque must be verified. The closed-loop flow starts with LDR light detection. ESP32 compares the sensor values. PCA9685 sends PWM signals, and the servos move the panel. Firebase handles commands and monitoring while real-time tracking stays inside ESP32.
Hello, my name is EREN. I'm the software engineer of our team. First, I'll be talking about our mobile app workflow. Firebase Cloud is used as the communication layer between smartphone and ESP32 so that control and monitoring is possible regardless of proximity to the device. There is 2 branches in the database structure. Control branch stores mode, manual direction, and command time. ESP32 reads these commands and sends monitoring back to database to monitoring branch. The mobile app allows automatic tracking, manual tracking, and stopping the device. It also shows monitoring data. Real-time tracking still runs locally on the ESP32 for reliability. A model for our application is shown here. The system has different operating states. In automatic mode, LDR data is read and the panel is directed to stronger light accordingly. In manual mode, the device follows phone command. In error or low power cases, the device moves to safe stop state. Now I'll be talking about our test planning. First, unit tests are done. In these tests, each component is checked individually. Then module tests are carried out for command and monitoring. Then the functional tests are done to check if auto tracking, manual control, and warning safe mode is working. Finally, the integration test is run, which verifies the full loop. To conclude, our design combines ESP32 local tracking with smartphone control, making the design user-friendly and reliable. The main remaining issue is to verify the servo torque for the 50 watts panel. Thank you for listening.